Hello everyone, welcome to this new video. So in this today's problem, we shall see a combination type of problem again. So one is from the concepts of probability and the other one is from the concept of triangles. So the very first question ranges from the difficulty level of medium to hard. Fine, it depends upon the logic. So basically the logic that I have taken here is so significant and will be helpful for many of viewers to tackle some other type of problems. Fine, this logic will help them. And the second one is also the same thing, like it's a little bit conceptual one. So it's a direct formula type or theorem, something like that. So you don't need to think much while tackling this type of problems if you actually know the logic behind this. So that's the reason I've taken this problem. So that's the main reason behind listing this combination problem, the difficulty level of this combination problem as hard. Fine. So the overall thing, to be honest, the overall difficulty level will not be hard. It will be ranging from the medium to hard, but the logics that I'll be teaching you here will be helpful to tackle other problems. That's the reason. Okay, so so this question says, if the simplified value of the probability of choosing 7 different numbers from 1 2 3 so on till 22 is 90x divided by 919. So fine, so x is the unknown value here, y is the unknown value here, this is 0. So 90x divided by 919, 9 by 9, given that there are at least 2 adjacent integers among them. So if you choose like 7 different numbers you need to choose, and it's a important condition that at least 2 adjacent integers, that means there will be at least one pair, like some integer, like if I assume a comma b, then at least one pair like this where a and b should be adjacent integers. Fine. And if 2x by y simplifies to alpha by beta, and gamma is the length of the hypotenuse of a right angle triangle in which alpha beta are the lengths of legs of the right angle triangle. So for example, if we construct a right angle triangle, then alpha and beta will be the legs, so they can even interchange, like this can be beta and this can be alpha even. Fine, but the hypotenuse will be the same, isn't it? It will be gamma itself. So then find the value of the diameter of the incircle of this right angle triangle. So you just need to find the diameter of this this circle. So there are various formulas, even there are direct formulas, like small r in terms of ABC, you can do it and all the stuff, and then multiply it by 2 to get the diameter. So there are various theorems and all the stuff, but what we shall see here is a very interesting thing, like very interesting formula, so by which you can actually get the diameter within seconds. Fine, even seconds takes a lot of time. It takes maybe 1 second or 2 seconds hardly. Fine. So yeah, that's how you can solve it. So let us assume, let us proceed now. So the thing is, let us assume a1 a2 a3 a so on a7 are the numbers that are chosen, such that a1 is less than a2 and less than a3, less than a4, less than a5, less than a6 and less than a7. Fine, so this is how the numbers are chosen, like these numbers. So whatever maybe it is, so you can randomly choose any number. So if I choose 5, so let me so if I take this color, fine. So if I choose 3, and this is 1, this is 2, this is 4, and this is 8, and something like that, whatever set of 7 numbers you choose, you can actually rearrange them in this way, isn't it? You can actually rearrange them. So that is the reason we have did it. So it's not like the a1 that we have taken, or what do you say, you can just rearrange them. That's what I'm saying. So you can put a2 to be 1, a1 to be 3, and a3 to be 2, and later on you can just rearrange them, right? So that's what I'm telling you. So such that a1 is less than a2, less than a3, less than a4, less than a5, less than a6 and less than a7. Now, if these are not adjacent, fine. If these numbers are not adjacent, then this is a limiting case. Fine. This is how you actually need to think to solve this problem. So you are just reducing the stuff. You're like, if I've given you a problem to deal with this much of stuff, you are actually reducing the stuff to this much. Fine. So the size of the problem has been reduced, but the concept remains same. So that is the logic that we are using here. So if a1, a2, a3, a4, a5, a6, a7 are not adjacent, then 1 less than or equal to a1 is less than a2 minus 1 is less than a3 minus 2 less than a4 minus 3 is less than a4 minus 4 is less than a6 minus 5 less than a7 minus 6 is less than or equal to 16. How did I get this? So if I take some 7 numbers, so let us assume 1, 3, 7, 9 and 12, and so 1, 3, 7, 9, 12 and 16 and 21. Okay, so these are the numbers that I have taken. So now, like, this would be a1, this would be a2, this would be a3, this would be a4, this would be a5, this would be a6, this would be a7. So I need to arrange them in this fashion, right? So that's the reason I've got this. Now this is a1, fine. Now 1 will be less than or equal to a1, isn't it, because it's 1, and less than a2 minus 1, 3 minus 1, 2. How did I get this? Because 1 and 3, 1 is less than 3, isn't it? 1 is less than 3, and also 1 is not adjacent to 3. 1 is not adjacent to 3. That means there will be lying an integer in between 1 and 3. And if that is the case, 1 shall be less than this integer even. So that is the reason a2 minus 1. And now when you are reducing a2 by 1, then you can even reduce a3 by 2. Fine, you can even reduce a3 by 2, and these are all the limiting cases. Fine, you can even reduce a3 by 3 also, but that doesn't mean it will be valid all the time. But a3 minus 2 will be valid all the time. Fine, so 7 minus 3, that is 7 minus 2, that is 5. So 5 is greater than 2, that is 8, this one value is 2 and this value is 5 and this value is 1. So 1 is less than or equal to 1 is less than 2 is less than 5, isn't it? So this is how it is. So when you're actually reducing the number by 1, because they are less and also they are not adjacent, so that's the reason if you reduce a number by 1, it will not affect the inequality. And now when you're reducing the number by 1, you can even reduce the others, the greater part of the inequality by 2. The inequality doesn't change because these are not adjacent. This is the very important point that you need to remember. The same thing applies over here, over here, over here, over here also. So if you substitute all these things, a7 minus 6, that is equal to 15, and if you choose a7 to be 22, 22 minus 7, that is 16. So that will be less than or equal to 16 because equal to sign is there here. So this is how we can construct it. Fine. So I hope this whole logic is clear. If it's not clear, just replay the video. Okay, just go through the video once again. So it's a very important logic. It's like you're tackling this big problem in a smaller version with the same concept being applied and getting the final answer to be same. The final answer that you'll be obtaining if when you do this and when you do this will be the same. Fine, that's how we'll see here. So we can say that choosing 7 non-adjacent numbers from 1, 2, 3, so on, this is 22, is same as choosing 7 different numbers from 1 to so on till 16, that is 16C7, isn't it? Because we have reduced the stuff, like we have reduced like these are 22 pile of numbers, these are 16 numbers, fine, and choosing 7 non-adjacent numbers from here is same as choosing 7 different numbers from here, because we have defined the inequality such a way that none of them are none of them are adjacent, and also they are following the inequality. They are following like each number, like a1 is less than a2 minus 1, is less than a3 minus 2, and so on. Fine, we are getting different numbers and none of them are adjacent, because you can see none of them have an inequality sign. You can just leave the last ones because these are the limiting, these are the maximum and minimum. So these are the 7 numbers that we need to consider, because we are asked to choose 7 different numbers, not 9 different numbers. So we cannot include 1 and 16. So we are limited to these conditions. Fine. So in these conditions, we have actually reduced 22 number to 16 number, and to choose 7 non-adjacent numbers from 1 to so on to 22 is same as choosing 7 different numbers from this pile, isn't it? So that is the reason. And what's the problem, different combinations of choosing 16 7 different numbers from 16, that is equal to 16C7. Now therefore the required probability is 22C7 minus 16C7. Why are we actually subtracting it? Because there are actually 22 set of numbers, and from that we need to choose 7 different numbers, and that if we subtract all those conditions, all those numbers from where there are no adjacent numbers, fine, and if this is a pile, like in this pile, if this is a pile where there are no adjacent numbers at all, then we can actually get this will actually result in such a pile resulting pile where you can find at least one pair of adjacent numbers. Fine. So that is the logic. I hope you are getting it. So adjacent numbers. So this is the logic. So if I subtract this pile from this whole big pile, will be resulting in this pile in which we can actually get a at least one pair of adjacent number, at least one pair. So these are all the conditions. This is a condition in which there will be, you will be finding no adjacent numbers, and this is actually equal to, so take the reason why we have kept this 16C7 as the answer of no adjacent numbers at all, because this is actually equal to choosing 7 non-adjacent numbers from the 1 2 so on till 22. Getting my point? So from the original set 22 numbers, choosing those numbers, choosing 7 different numbers which are not adjacent at all, like you will be finding no number adjacent, is actually 16C7. That is, we have reduced this big problem to small problem and we have solved it. So when you subtract this, you'll be getting 159104 divided by 170544, and that is equal to 904 by 969. And when you actually see that this is the simplified version, you cannot simplify much later or much further. So you get x is equal to 4 and y is equal to 6, and this is how you do it. I hope you guys actually understood this. This is a very fantastic logic. So this is how you can actually apply in other like like in computer knowledge you say this as recursion and something, but this is like you're reducing a big problem into a small pile of problem and then you're doing it. Fine. This is how you need to think about it. And the important condition is here at least 2. Fine, at least 2. That is the reason we have actually confined this to 1 and 16. Like only we have only did this minimization for only for ones. And now 2x by y is equal to 8 by 6, which is equal to 4 by 3. So the legs of a right angle triangle of the required triangle 4 and 3. Therefore the hypotenuse will be 5, isn't it? Now this is a so-called I would say the theorem. So if AC are the lengths of the legs and B is the length of the hypotenuse of a right angle triangle, then A plus C will be equal to B plus D. So this is, in our case it will be 4 and this would be 3 and this would be 5. Then D is the diameter, that is the required thing in the question, like that is the thing that we have been asked. So this would be 4 plus 3 minus 5, that will be 2. Fine. So this is how you do it. Just a second, it takes 1 second or 2 seconds. Fine. So the proof, this proof also is so easy, but so you can take a right angle triangle and you can inscribe a circle in it, and you can actually see here because you can say that from a point outside the circle, if two tangents are drawn, the intersection points, and let the intersection point be D and F, then we know that BD will be equal to BF. Fine, we know this important theorem, important like what do you say, theorem in the part of circles. So this would be equal to x, this would be equal to s. From an exterior point, two tangents are drawn and the intersection points and D and F, then the distances between the point to the intersection points will be the same. So it would be BD would be equal to BF is equal to, that is x in this case, and AD will be equal to AE will be equal to C minus x, because this is C in the opposite vertex. So this total distance is actually C, and this is x, this would be C minus x. And because this is C minus x, this is also C minus x. Again, an x, two tangents are being drawn from the point A. And the same thing here it lies. So this whole distance is A, and because this is x, this is A minus x. And because this is A minus x, this is also A minus x. So you can just add them up, like A minus x is plus A minus x plus C minus x, which is actually equal to B, because this total distance is equal to B. Fine. So if that is the case, we can just write A plus C is equal to B plus 2x. This x and this x goes to the other side. So A plus C is equal to B plus D. And why is D is 2x? You can just see here, this is the radius, right? This is the radius. And what is radius? Which is equal to x. You can see a square being formed here. So this is equal to x is equal to D by 2. So 2x would be equal to D. So that is the reason A plus C is equal to B by D. So you can just substitute, you will be getting D is equal to 2. That is the diameter. So this is all for today. I hope you actually enjoyed this. So very interesting problem theorem, like interesting, what do you say, the interesting way to solve this very first question is this. So you can actually minimizing the stuff of the like very big stuff into small stuff, and then you're applying the same logics. Fine, this is how you do it. You're actually minimizing the numbers, minimizing the stuff, and then you're applying the concept and getting the same answer that is actually required. You're not even doing any other stuff. You're actually getting the same answer that is actually required. So and then subtracting them so that we get the required answer, that is at least two adjacent numbers, like at least one pair. That is the required thing. So I hope people enjoyed this problem. So thank you for watching. Stay tuned.